Now, this video is only for high-level IB students, so please ignore it if you've come across it. Basically, what we're trying to do is work out the entropy, how much extra randomness there is when ice turns to water. And that's because at 0 degrees, the ice and the water will be in equilibrium. So the delta G will be negative. It won't be going in one direction or the other. So we can sub that into Gibbs' equation and get this. And so the entropy will be what the change in heat is between ice and water at the temperature at which it does it, which is 0. So there'll be whatever the delta H at 273.15 is. And so that is that equation right here. And that's the heat that it takes to change from ice to water. And that's called entropy of fusion. So entropy of vaporization, or latent heat of vaporization, is liquid to gas, gas to liquid, and we're looking at the latent heat of fusion, which is the amount of energy it takes from ice to go to liquid or liquid to go to ice. And so once we've got that number here, and I actually end up getting a 1% error using their calculations, then we divide it by 273 and you'll get that value, and that's the correct answer. The correct answer is 22. All right, so it takes 22 joules per mole Kelvin, and that's the entropy of water. And so I'm going to leave it in a fairly messy state because the value of it comes from you working through those calculations yourself. And when you do that, I'll show you at least one major error in their calculations, but I think there's a second one, and I want you to be able to think of that, and I want you to be able to perhaps even work out these calculations without looking at this sheet. But I will upload this sheet to the website, so you've got this method here. And so you can see, I'll just briefly show you me doing the method. So I put about 400, I just heat water up to about 50 degrees. So I follow the method exactly, and then I put about 100 mils of that water in a measuring cylinder and just use a pass-through pipette to get it to exactly 100. I want the calculations as neat as possible if it's easy to do it that way. And then I put it in a styrofoam, a stubby holder, a bic with a stubby holder on it, just some insulation, and that's the number I get, 45.7. And then I put some ice in there. Okay, so I'm just doing exactly what it says. I did measure out that about 3 cubes is about 50 degrees, so I kind of knew that, but I had to put a fourth one in there anyway to get it down to about 0 to 4 degrees. And so I keep stirring it until it gets to that level. When it gets to that level, I remove the ice and I read off the data logger that it's down to 3.3. And then I put all the water into a measuring cylinder, and conveniently it's exactly 50 mils. That's super convenient, just by chance. Okay, and so just plugging in the numbers according to how they have plugged the numbers. I just put them side by side. I worked out I actually did this one wrong. It's like 600 and something when I was properly analysing what they were doing. So I'm down to a 1% error, and it looks fine and dandy. So I want you to do that experiment and then do the calculations and see what you get, and hopefully you can find the mistake. And so my calculations are here trying to make sense of it, just trying to be clearer. This may help you a little bit. So 100 mils of melted 50 mils of ice decreased 100 mils of water from this temperature to this. I don't really care about this assumption here, so they're just being extra careful, making sure that the not just assuming 100 mils is 100 grams, but it's pretty close. It's less than 1% error here and 0% error here, so it's a small thing. So I was happy with that calculation. I was happy for them to not be so pedantic on this mils to grams assumptions, and I was happy with this assumption. My huge assumption that I think, and that's just the first mistake, you have to think of the second one yourself, is the ice is varying temperatures, and it takes energy to cool the ice to 0 before it starts doing the temperature change. and that's not taken into account, I don't believe. So I did that sort of calculation and got a different result. And I don't think loss to the environment is significant because the heat's cooling down and the cold's warming up, so it might cancel each other out. But it's, if you can see from the graph from the data logger, it's not super significant, the changes in temperature. And I did put the data logger onto a piece of ice. I didn't put in that video there, snippet, to see what the rate of heating was. So that could be taken into consideration. But there's another massive error on top of that as well, and they're missing another calculation as well. And so anyway, using the corrected formulas, using their original formulas, I only get a 1% error, but really I need to do it with this value, and not even that. Hopefully you can tell me, write it in the comments, what you think the second error is in their calculations, and whether or not you agree with me that Flynn Scientific, a huge scientific company, has made a major error in their calculations.